All right. Hello, everybody. My name is Ryan Thurston. I'm part of the Worldwide Specialist Organization for Amazon Web Services. I'm joined by my colleague, Karthik, and today we're going to talk to you about global clusters. We'll talk briefly about what is Amazon DocumentDB. We'll do an overview of the architecture, and then I'll hand it over to Karthik, who can talk a little bit more about global clusters and then provide a demo as well. Before we jump into the service, I just want to take a step back and show the broad offering of services that we have across databases and analytics. The service that you use will typically depend on the use case. We call these purpose-built databases. And broadly speaking, we have a variety of different database services. We have relational databases. These are for customers that want to move away from self-managing Oracle or SQL Server workloads and move them into AWS. We have Aurora and RDS for those types of workloads. And then we have a segment of databases called our non-relational databases. And this is actually where DocumentDB fits in. These are for customers that want to move away from self-managing their Mongo databases, Cassandra, Redis, etc. And then the remaining services on the right are our analytics services that can be utilized as well. All right, so what is DocumentDB? It's a fully managed, scalable document database service that supports MongoDB workloads. It's fully managed. It's managed by AWS. There's no hardware to provision. It's easy to set up through the console. You can spin up a cluster in minutes. There's built-in high availability. Clusters are automatically provisioned across multiple availability zones. Best practices are enabled by default, so backups are enabled. From a durability perspective, data is copied 6 ways across 3 AZs. And then from a security perspective, you can use identity and access management and built-in role-based access controls to enforce least privilege access. And then patching and maintenance are handled automatically by the service. And finally, we have native integration with CloudWatch for monitoring and setting up alarms, CloudTrail for logging and auditing, and other services to really help simplify your technology stack. And our customer FINRA utilizes DocumentDB without any overhead from their engineering teams. DocumentDB is scalable, so the separation of compute and storage allows you to scale both of these aspects independent of one another. You can scale compute horizontally or vertically in minutes, regardless of the amount of storage in the cluster. Storage and I/O autoscale from 10 gigs all the way up to 64 terabytes, so there's really no need to worry about taking care of a EBS volume as you would in EC2 or scaling an on-prem SAN. And you can scale out to up to 15 read replicas in a matter of minutes. Our customer Iron scales their clusters in minutes regardless of the amount of data in the cluster. We're MongoDB compatible, so we're compatible with the MongoDB version 3.6 and 4.0. You use the same SDKs, tools, and applications. We support hundreds of APIs, operators, and aggregation stages, and we work backwards from our customer. We start with you, we get feedback on the product, which is then fed back into our engineering teams to implement feature requests. Our customer Freshworks love the fact that we are compatible with MongoDB. Their application required 0 code changes. Now, when would you use a document database? Probably the most important is when you're working with JSON data. So document databases store data in a JSON-like format, which is flexibly structured and really maps naturally to how we think about modeling data in our heads. We typically don't monitor it in a tabular format, but we're thinking about groups of things instead. When you have a requirement for a flexible schema, with document databases, there's no need to design a complicated, rigid schema. The schema can change depending on your data needs and access patterns. When you have a requirement for ad hoc querying capabilities, whenever you need to retrieve specific fields and values and work with regular expression queries, DocumentDB uses a JSON-like query language, so it's really easy to learn. And when you have a requirement around flexible indexing, so within DocumentDB, indexes can be created and dropped on demand and can be declared on any field within your documents, including fields nested within arrays. And we have a lot of customers across a lot of different industries and verticals. We've been GA since January of 2019. We have customers running production level workloads, anywhere from small startups to Fortune 50 customers that use DocumentDB for their production workloads. In terms of use cases, there's really a broad spectrum of use cases that are associated with DocumentDB. Content management. So a lot of the content that you read today, from news articles to blogs to recipes to patient records, all of that data lends itself really well to a document model since it's dynamic and changing. Mobile is another great use case. So it's really easy to store the data you're collecting going back and forth between devices. Catalogs, being able to record the outputs of machine learning experiments, inventory descriptions, pharmaceutical trials. We see a broad set of customers that use documents for these types of use cases. And then gaming, storing user profiles, game management, and matchmaking. Really, anytime you have a complex document that requires nested indexes, ad hoc queries, etc., that's really a good example of when you might use DocumentDB. I want to talk a little bit about Rappi, who is a customer of DocumentDB. They're a Colombia-based startup that's similar to DoorDash in the US. And they built up an app that handles restaurant orders, groceries, and other orders. And their business problem was that they had such a popular restaurant delivery app that the service experienced frequent outages, sometimes 3 to 4 hours of downtime during peak service times. They had built a monolithic application and needed to support a more flexible microservices-driven approach. And their slow performance affected thousands of users, and queries sometimes took up to 500 milliseconds. So they were looking for a database that was compatible with MongoDB. They also needed to independently scale their microservices. Their current architecture had one Elasticsearch cluster for all of their 9 business units for each country. But most importantly, they wanted to get out of the infrastructure management business and eliminate what we call the undifferentiated heavy lifting of maintaining infrastructure for multiple MongoDB clusters. So their solution was to create a single cluster per business unit and utilize their ability to scale using microservices. The horizontal scaling of read workloads reduced their query latency from 500 milliseconds down to 80 milliseconds. And with minimal code changes, they were able to migrate from MongoDB to DocumentDB, resulting in a 60% FTE cost savings. And some of the solution advantages. So, before Rappi had a bunch of outages in the past, and they had a lot of scaling and performance issues. But since migrating to DocumentDB, they've had no outages. Their largest cluster took about 2 weeks to migrate, and they afterwards were able to perform over 100 migrations in under 3 months. But most importantly, again, going back to cost, Rappi now only has a handful of engineers that are managing this deployment compared to the dozen or so that they had before. And this reduced their operational overhead by 50%, allowing them to focus more on value-add activities. All right, I'll transition this over to my colleague Karthik, who can talk a little bit more about the architecture for Amazon DocumentDB.
Thank you, Ryan. Ryan talked about what is DocumentDB and discussed about the use cases. Now let's talk about DocumentDB's architecture that provides durability, scalability, and a global footprint. So this slide shows DocumentDB's architecture for a regional cluster. DocumentDB is architected to separate storage and compute so that they can be scaled independently. The compute instances can be scaled horizontally or vertically, and they are distributed across 3 availability zones for high availability. And to maintain high durability, DocumentDB replicates data 6 ways across 3 availability zones in the distributed storage volume that you see on the screen. DocumentDB's architecture allows us to offload tasks to the respective layers. Now, for example, replication task is offloaded to the storage layer so that your compute resources can be freed up to perform compute-heavy work, such as query processing. Likewise, backup is another task that is offloaded to the storage layer, further freeing up your compute resources to perform those compute-heavy work, which pretty much is what your application would demand from a database. As a reminder, DocumentDB is a fully managed service. This means that AWS manages these tasks and ensures that the data is fully replicated, allowing you to focus on developing features that matters to your customers. Now that we understand how DocumentDB is architected for a single region, let's take a look at the architecture for global cluster. Amazon DocumentDB global clusters allows you to replicate data to up to 5 read-only secondary regions. You can send the write operations directly to the primary cluster, and DocumentDB automatically replicates this data to secondary clusters in different AWS regions using dedicated infrastructure. Like before, replication is offloaded to the storage layer. We talked about this in the previous slide. Same thing applies at the global cluster level as well. And this replication is a physical replication from the storage layer in the primary cluster to the storage layer in the secondary. And hence the replica lag is very low. Typically, we see it to be less than a second. Global clusters allows you to recover quickly from regional outages. Now, should they happen, right? But if they do happen, that is a feature that global cluster provides when it comes to recovery. And if you need to fail over to another AWS region, you can promote a cluster in a secondary region to a standalone cluster that can accept writes. And this process typically takes less than a minute. So, global cluster is ideal for applications with strict recovery time objective requirements, or RTO, as we all know it as. Now, as you can see in the slide, we have a global cluster with 2 secondary regions, one in Tokyo and the other one in Oregon. And the primary region is in Ohio. Application 1 writes the data to the primary cluster in Ohio, and application 2 reads this data from the secondary cluster in Tokyo, typically in that 1 second or lower than that time frame. Now, there are a few things you need to know about this feature. First, global clusters are compatible with DocumentDB engine version 4.0. So if you're running on a lower version of DocumentDB, which is 3.6, you'll have to upgrade to the new engine version to use global clusters. Second, if you deploy global clusters to all the 5 AWS regions, which is the maximum number of AWS regions you can replicate the data to, then the maximum number of reader instances you can run across these 5 secondary regions and 1 primary region is 90. That is a significant number of instances to allow you to scale reads globally. I'll now demonstrate how to create global clusters. And let's get into the AWS console to see how you can start with global clusters. All right, so I'm here at the AWS console, and I'm in the Ohio region. I have a couple of clusters here. I have 2 regional clusters and 1 global cluster. I'll walk you through this global cluster, but before I do that, let me start with the regional cluster, and I'll show you how to create a global cluster. So you would start with the regional cluster and convert it into a global cluster. So I have a regional cluster called cluster 1 in US East 2, which is Ohio, and I'm going to convert this into a global cluster. So I select this cluster and I say add region. And now I'm going to say I want to create my secondary cluster in Northern Virginia. I'm going to give this global cluster an identifier. Since this is the first time I'm creating a global cluster, I need to give an identifier to the global cluster. So I'm going to call this global demo, and I'm going to give a cluster identifier for this cluster in Northern Virginia. I'm going to call this as cluster 2. And I'm going to leave the instance class as R5 large. I can choose a different number of instances to be running in the secondary cluster. To be frugal, I'm just going to say 1 instance. I can also do 0 and make it headless, which I'll talk about in a bit. And that's pretty much it. Now I can say create cluster. And this process will take about somewhere around 8 minutes to 10 minutes to create a global cluster. So I want to quickly walk through what has happened here, right? Since we started. So we started with this cluster 1, which was categorized as regional cluster, just like this regional cluster over here. And then we said add a region, and we call the global cluster identifier as global demo. And you see that we now have a role called global cluster, and our cluster 1, which was the regional cluster before, is now categorized as a primary cluster. And then we have our cluster 2, which we just created in Northern Virginia. This is categorized as a secondary cluster. And you can see that the cluster 1 is modifying in modifying status, meaning it's modifying itself to get ready to replicate data to cluster 2 when it changes its status from creating to available. Now, I said that you can have up to 5 secondary regions. So how do you add more regions to it? So earlier we started with cluster 1. Now that we have a global cluster, you select that global cluster, go to actions, and say add region. Now I'm going to say I want to replicate the data further east. Let's say I want to go all the way to Mumbai and replicate the data. I'm going to call this cluster in Mumbai as cluster 3. And again, I can select different number of instances. Just for a change, I'll select 2 this time and say create. Right, so this will add one more secondary cluster to our global demo cluster. And so in total, we'll have 1 primary and 2 secondaries. Now, again, I can add another 3 more actually secondary clusters to this to reach the max. Right, so here I have like one global cluster with 1 primary and 2 secondary clusters. And those 2 clusters are in creating status. Like I said, it takes about 8 to 10 minutes to get those clusters created. And to save time, I created this global cluster demo to show you what it would look like once it is created. So I have very similar configuration here: 1 primary called demo 1 with 3 instances, and then I have a demo 2 running in US East 1, which is Northern Virginia, and then I have a demo 3 running in AP South 1, which is Mumbai. So now I can click on this cluster, and then it'll open up the cluster view for it, and I can see that I have like the connection string to connect to this cluster, very, very similar to what you would see in a standard regional cluster. If I go back to the cluster view and click on my secondary cluster, you can see that it opens in a new tab, automatically switches to the region, which is Northern Virginia, and it gives you the connection string, which has the -RO in it, indicating that this is a read-only cluster. Now, keep in mind, all the secondary clusters that you're going to be creating through global clusters are going to be read-only. So you see this cluster view here, and you can copy this, and you can read data from this cluster that is being replicated from the primary. Likewise, if I go to my demo 3, it opens in a different tab. It switches the region to Mumbai, and it shows me the cluster view with the connection string, which again has -RO. So that's pretty much what I wanted to show for this demo, which was about creating a global cluster. And we saw how we start with a regional cluster and then convert it into a global cluster and add additional secondary clusters to it. So we'll come back to this global cluster for a subsequent demo here in a bit. But for now, let's go back to the presentation and look at some of the best practices when creating global clusters. So let's look at what are the best practices you should follow when you're creating global clusters. We typically recommend customers to use an identical cluster parameter group for the primary and secondary clusters inside a global cluster. Also, it's a best practice to size instances in the primary and secondary clusters to be of the same size. So I created my primary with R5 large. It's a best practice to create secondary with R5 large. Now, the number of instances doesn't matter, but the size of the instance. It's always the best practice to keep them in sync so that the cache hydration and the time to restore during DR would all be predictable. And also, it's a best practice to externalize your database connection parameters, because this helps to switch databases without application changes. Your application can point to one database now, and you can easily switch to another if you externalize the database connection parameters. And this makes failover process simpler during a disaster recovery scenario. And when you're performing failover, there are a set of steps we recommend that you follow in order. The first one is to stop the application from writing to the primary to avoid any data loss. Then identify the secondary cluster to promote, and this is going to be based on the acceptable latency for your end users. Once you have identified this cluster, remove and promote the identified cluster, which is going to be a secondary cluster, to a standalone primary cluster. To do this, you can use the console, the CLI, or the SDK. And after the promotion process completes, point your application to the new primary. You can, if needed, add additional instances to this newly converted cluster and convert it into a global cluster like that. And then you can delete, as a last step, you can delete the old primary and the other secondaries that are associated with that global cluster to save cost and avoid reading stale data. The steps outlined to promote secondary cluster and deleting the old primary and other secondaries can be easily automated using shell script or Lambda functions. I'll show you one such script towards the end of the session today. So we've discussed what is a global cluster, how to create it, and the best practices. Now let's talk about the use cases for global clusters. The common use cases for this feature are disaster recovery and data locality. Let's start with disaster recovery, right? By adding additional secondary regions, you can configure your deployment for disaster recovery and seamlessly promote secondary clusters to primary. And I'll show that to you in a bit here in a demo. And this promotion process typically takes less than a minute. So you should, again, this is when a AWS region failover happens. If and when it happens, you can typically failover in less than a minute for faster recovery. By replicating the data to secondary clusters in real time, applications that have users distributed across the globe can benefit from local reads, and they can avoid regional latencies by reading data from a secondary cluster that is closer to their AWS region. We'll double click into both of these use cases now. Let's start with DR. Right? So DR is a very common use case for global clusters. Since the data is replicated in near real time from the primary to the secondaries, global clusters allow you to be up and running in the secondary region in less than a minute if and when a regional outage occurs. Now, there is no data movement that needs to happen when you're performing a global failover. The time it takes to recover is just the time it takes to promote a secondary cluster to a standalone cluster. Also, use cases where you want to migrate data across regions are easily solved by this feature, global clusters. One of the important points to note here is the cluster topology. Your primary cluster will be running the required number of instances to satisfy your application's, let's say, SLA and the availability target. Since replication is offloaded to the storage layer, the instance count for a DR cluster need not match the primary region. I showed this to you in the previous demo where I was creating a global cluster with different number of instances for each of the clusters in each of the secondary clusters. You can set up a DR cluster with just one instance and still get the low replica lag and high durability in the secondary region, thanks to the decoupled architecture that DocumentDB has. You also have the option to use headless clusters in the secondary region. If you recall, when I was creating the global cluster, there was an option to select 0 instances. So that is what I'm referring to as headless. Basically, you can run the secondary cluster with no instances at all. Thus, offloading replication to storage helps with cost optimization in addition to low replica lag. Scaling your secondary cluster will take about 8 to 10 minutes, regardless of the data volume, due to the decoupled compute and storage layers. And now let's talk about data locality. Since replication is offloaded to the storage layer, there is little to no impact to your application performance because your applications typically interact with the compute layer and they do not participate in this replication. And the low replica lag of less than a second enables you to use these secondary clusters to perform local reads, thus enabling you to build globally distributed applications that can read data from clusters that are closer to the end user's region and thereby avoiding those cross-regional latencies. I'll now demonstrate how to perform local reads, and I'll also show you how to promote a secondary cluster to a standalone primary. Now, this failover process that I'm going to demonstrate is manual, but it can be easily automated by leveraging AWS CLI or SDK. And I'll show you a shell script that you can use to automate this failover process as well. So let's jump into the AWS console now. So let's now go to the terminal window to look at the application servers that I have. So I have 3 EC2 instances, one in Ohio, one in Northern Virginia, and one in Mumbai. Again, my primary DocumentDB cluster is in Ohio, and the Northern Virginia and Mumbai has secondary clusters. So I have, let me show you what I have in this application, what application I have running here, right? So I have a sample app.py, which writes in the Ohio region, and the sample app.py reads the data in the Northern Virginia and Mumbai region. So before I can run the sample app, I need to provide an endpoint, right? So this application uses an environment variable called endpoint. So I'll export the endpoint for each of this region. So let me start with my Ohio region. So I'm going to say export endpoint for the demo 1 cluster. So demo 1 is my primary cluster. I'm going to export this endpoint here, and I'm going to export endpoint for my demo 2 and demo 3 clusters as well. So demo 2 is in the Northern Virginia region, and demo 3 is in Mumbai. So now through this, I'm telling my application which DocumentDB cluster they should be interacting with. Now that we did that, we are ready to run the application. So I'm going to say Python 3 sample app.py, and you can see that all that this application is doing is on the Ohio region, I wrote 5 documents, and I'm reading that in the Northern Virginia and Mumbai region. So let's look at the last document inserted here. So this was inserted at 32.43 seconds. And here in Northern Virginia, we read that at 33.13, which is again less than a second. And here we read it at 32.22, which is again less than a second. So again, this is round trip, not just the database level replication, but round trip all the way from between the application and database, right? So it is typically, like I said, it's typically less than a second. It is less than a second, not just for the database replication in this scenario, it's also for the round trip. So that is how the data locality use case would work. So you can easily read the data in the Northern Virginia and Mumbai region that is being written in the Ohio region here, right, in the primary cluster. So you can use the near real-time replication and provide access to the data to your customers without them having to go across the regions or go through the cross-region latency. Now, let's look at our second use case, which is disaster recovery. So let me go back to the AWS console here. So let's say that the US East 2 Ohio region, where our primary cluster is, let's say for whatever reason this cluster is not accessible. Maybe the region is down, or the database cluster is not accessible for whatever reason. Now, what do you do, right? So again, in such cases, you can promote a secondary cluster to a standalone primary, and this will help you to with your business continuity, right? So you can start using the secondary cluster. Once it is promoted, you can then start writing into data into that cluster. So how do you do that, right? So here I select this cluster. Let's say I pick this cluster because obviously this is going to have the lowest latency compared to the Mumbai cluster, because right now my primary is US East 2. So I'll pick my US East 1 and I'll say that, hey, I want to promote this cluster into a standalone primary because this primary is not available for whatever reason. So I go to action and I say remove from global. And when I do this, when I click on this remove and promote, it does 2 things, right? It first removes the secondary cluster called demo 2 from my global cluster called global cluster demo. And then it promotes the demo 2 secondary cluster into a standalone cluster, or in other words, into a regional cluster. So I'm going to click on this, and you can see that you get a message that it says removing and promoting your cluster demo 2 from global cluster demo, right? So this is your global cluster identifier, and this is your regional cluster or secondary cluster identifier. So again, like I said, this process takes about 1 minute or less. So you can see that I'm just refreshing to see, okay, yeah, this is now in a status called promoting. And in about a minute or so, you would see that this cluster demo 2 would be out of this global cluster. So you would not be able to see this over here, because now that becomes a regional cluster and its region is in US East 1. So you would see that cluster only in US East 1. So let's refresh to see what the status is. So now you can see that the demo 1 cluster is in modifying status because it's no longer going to be replicating the data to the demo 2 cluster because it is being removed from this global cluster and being promoted to a standalone primary cluster. So refresh it again, and it is still in motion. So like I said, it takes about a minute or so. And in the meantime, let's click on this demo 2 cluster, and we'll go into this region, which is Northern Virginia region. And you can see that it is still in promoting status. And you can see that it has already changed the endpoint, which had -RO before, because -RO indicated that it is a read-only cluster. Now it no longer has that -RO in it, meaning this cluster is again, it is still in promoting status, but it is the endpoint does not have that -RO, indicating that it is going to become a cluster to which we can write data into. Right, so let's refresh to see what happens. There you go. The cluster is in available status, and it is. If I go to this cluster view over here in Northern Virginia, I still have the global cluster demo because you can see global cluster across all the regions, and I have inside that global cluster demo 1 and demo 3. No longer demo 2 is a part of that global cluster. Instead, it is now a regional cluster, right? And again, it has one instance. And this instance is basically, the one that we created before. And obviously, since there's only one instance, it will be categorized as a primary instance. So this is R5 large, and let's go back to this cluster here, and let's look at it from this view, instances, and it's a primary instance. So now let's go back to our terminal. And before I go back to the terminal, I'm going to copy this connection string just to show that this cluster, I can log in and I can write data into this cluster. So I copied the connection string for the cluster that I just converted or promoted to standalone. And here we can confirm that demo 2 is no longer visible in the Ohio region. So let's go to our application server over here, and let me connect back to my EC2 instance. And now let me clear the screen, and I'm gonna connect to this cluster, which I just promoted. Password, and you can see that it comes with a prompt called R0 primary, indicating that this is now, I can write into this cluster, right? So let me say show DBs, and you'll see there's one DB called test. I'm going to use test, and I'm going to say DB, let's see what the collection name is, show collection. It's called call. So I'm going to say db.call.find. Just going to find everything. So you can see that it has the data that was replicated to this cluster prior to the failover. Right, so I wrote 5 documents, and I can see that I have the 5 documents. So there's no data movement that happened, like I said before. Only the secondary cluster was promoted to primary. Now, if I want to insert data into this, I can say db.call.insert1, and I can say x. That and x1. And you can see that I inserted 1 record, meaning I'm able to write into this cluster, which was earlier a secondary cluster, now promoted to a primary cluster, right? And I can go and do find again, and you can see that this x1 is also written, and I have all the other data. So again, your application, from your application perspective, you are able to promote, and you're able to continue reading the data from the database and writing the data into this database. So that's how the disaster recovery feature would work. So typically in less than a minute, you'll be able to be up and running on a secondary region. Now, this process of promoting the secondary cluster, like I said, was manual, right? Like I use the console, but you can also use the SDKs or CLI. And if you guys are interested in using one, you can go into our samples repo, and you can find that there is a there is a shell script that I have here for you, and this provides the instructions on how to use it. Right? It's fairly straightforward. Just provide the global cluster identifier and the regional cluster identifier that you want to promote, and indicate if you want to delete the older global cluster or not. And then the script will basically go through the process that I just went through, and it will remove and promote your, in this case, Ohio cluster. And if you say Y like this, it will also delete the older global cluster. So I just wanted to share that with you in case you're interested in leveraging an automated script to perform this failover. So that's pretty much what I had for you in the demo. So let's go back to the presentation. All that we have left is time for Q&A now. So Ryan and I will be happy to take more questions that we might help answer.